All right, so how do we measure acoustic admittance? Okay, this is a complicated slide, but we're going to take our time with it and we'll be fine, okay? Reassurance, you'll be fine. What is this? This is the probe tip. This is the probe tip into the ear canal. Does everyone get that? So there's a cross-section of the ear canal. What's this thing here? The eardrum. And we've got this volume of air here into which our probe is sealed. Can everyone see that? What are the three components of the tympanometer? Well, we've got the thing which makes the sound. This is our volume velocity source. Then we've got a microphone to detect how loud the sound is in there, how big the sound is. And then we've got this syringe device to inflate that, push the eardrum back that way, and to deflate it, suck it back out that way a little bit. Okay, so we're going to spend a lot of time on this. Are you ready? So, imagine, so right now, if I talk loudly through here, can you hear my voice coming through the speakers? Can you hear that? So what is a speaker? It's a diaphragm like this, which has a magnet and coils of wire. You pass an electrical signal from my voice, from the microphone through the amplifiers to there. That fluctuating electrical signal pushes the diaphragm forwards and backwards like this, and that creates sound pressure changes which you then hear. So that's a speaker. There it is going like that. If that's moving like that and I cover the front of the speaker with wood, so I just block it off. Here's the speaker moving like this, and I've covered the front of it with wood. Is it going to find it harder to move back and forward because it's squishing up the air, or does it not care? It finds it harder. So it's going like this, and if it's free to move, yay, out goes the sound pressure. If I block it off, then it's going to find it harder, and it will be affected by that. So it doesn't produce as bigger sound. But there's a trick that we can do. If I cover the front of a speaker and then put a long pipe, just a thin tube, so the sound, instead of coming out of the hole of the front of the speaker, the hole of the front of the speaker is blocked except for a tiny tube, like this one. So a tiny tube comes out from a big speaker. What happens is the thing that is coming down the tube, where are we source, down this tube here, is no longer a sound pressure that is sort of stopped, like if I put my finger over the end of it would stop it. It becomes what's called a volume velocity source. So instead of just going like this, it's going boom, it's moving like this. It's sort of unstoppable. Imagine like an unstoppable slug of air, tiny bit of air moving backwards and forwards like this down the pipe. Can everyone picture that? So think of it as being something that's actually harder to stop than just a sound would be. So if you put your finger over the end of it, of course it's going to stop it. But if you did put your finger over the end of it, the sound pressure, the pressure in that pipe would get larger because you're trying to stop this unstoppable thing. Does that make sense? So if you're squishing the air into a volume, it's going to make the pressure go up. So imagine that. Imagine I had a volume velocity source, my speaker with the front closed off in a little pipe, and I stood outside the room over here, and there was a tiny hole in the door, and in came the little tube into here, and I had it going. Is that going to change the air pressure in this entire room by very much, my tiny speaker? No, because the volume of this is so big that it's just this tiny change, this amount of air that I'm pushing in, pulling out, pushing in, pulling out, is going to have no impact at all on the sound pressure we measure with a microphone in here. Does that make sense? What if I take that same device and put it into a very small cavity, like, let's say, your ear canal? So if I did that, if I put it into a much smaller cavity and ram that same volume of air backwards and forwards, am I going to record a pressure change in that tiny cavity? Yeah. Every time the air gets shoved in there, we've now got an increase in the pressure. And every time I pull it out, we get a decrease in the pressure. Does everyone see that? All right, so if I go push, pull, push, pull, push, pull, push, pull, and I do it very rapidly, 226 times a second, that's like a doo sound, what I'm going to get is, if the volume that I'm driving into is big like this room, I get basically no change in the sound pressure. But the smaller the cavity gets, the larger the change in the sound pressure becomes. Does that make sense? So I'm going to draw this out. Imagine I've got imagine I've got, here's my volume velocity, VV. It's called a volume velocity because it's literally a volume of air that is moving backwards and forwards with a certain speed. And it's a sine wave going like this. And this is the unstoppable bit. This is the, it's just like, imagine a piston on a train. 226 hertz is the frequency, 226 hertz. We use that frequency for adults. For children, we often go to a higher frequency for reasons that are beyond our purposes today. So that's what I'm putting into the ear canal. If I'm driving it into a big space, then the pressure that results from that, it'll be roughly in phase, but it could be a slightly different phase, but it's going to be like this. So that is that for a large volume or a small volume? Large volume. What about for a really small volume? What have I got there? A bigger pressure that I've recorded for my volume velocity. So I shove in a volume velocity. In one case, I get a small pressure. The next case, for a smaller chamber, I get a bigger pressure. What does the ear hear? What is sound? What is it sound that we're trying to listen to all the time? What is that? It's a fluctuation in pressure, right? So it's the red one. The red one here is sound, okay? I'm putting the same volume velocity into both chambers. What I'm hearing is, and the loudness of the sound that I hear will be dependent on the size of the red one. So which will hear a louder sound, an infant or an old man, if I drive that same volume velocity into their ear canals? Which one of these is the infant? Which one is the old man? Which one's the big one? This would be the infant, and this one would be the old man. So another way of saying that is this one is the small cavity. This one is the large cavity. Great. Okay, so I wish it wasn't blurring in and out like that, but yeah, you can see the difference in those two there. Okay, and that's at 226 hertz. Excuse my appalling handwriting. Okay, so one of those, the sound level will be louder. The one for the infant, the small cavity, they're going to hear it louder. Okay, now imagine I've got two cavities that are the same size. So, sorry, one cavity. Here's a cavity. And let's call it, it's like a tube. So here's a tube like this. And I put my probe in the end here like this. It's got those three pipes that are like that. And it's driving a volume velocity into this chamber. And it's measuring the air pressure that results. Now imagine that this end here is rock hard. It is basically like a brick wall at the end. We're going to get a certain amount of pressure build up in that cavity. Now imagine the same situation, same length tube, exactly the same length tube, same probe, like so, same pipes, and instead of a brick wall at the end, we've got a rubber balloon. Can you picture those two different scenarios? When I drive my volume velocity into this one and into this one, which one is going to have the bigger pressure change at the end? So imagine one of them, I'm driving the volume velocity into this space. So I'm driving the volume velocity into here, shove, 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 and it's got nowhere to go because there's a brick wall at the end. What happens to the pressure? It goes up and down, right? What about this one? I drive the volume velocity in, out, and this wall just goes out, in, out, in, out, in. Which one has the pressure got somewhere to go? Yeah, it pushes the balloon end out, in and out, in and out, in and out. Does that make sense? So am I going to get a bigger pressure change or a smaller change in the one with the balloon? Smaller. Am I going to get a bigger pressure change or a smaller one in the brick wall? Bigger. Great. So another thing which could tell the difference between a big pressure and a small pressure is not necessarily infant or old man or small cavity and large cavity. Those things are correct. But also, this one is hard wall and this one is some sort of compliant wall. And so hard wall, we say, is a high impedance, and a floppy wall is a low impedance. What's the opposite of impedance? I said a few slides ago, admittance. So high impedance also means a low admittance, and the low impedance is a high admittance. All right, very good. So there's some concepts. Does everyone get that? So what is producing the volume velocity? It's the speaker at the end of a long tube. Does everyone get that? That is producing our volume velocity, and it is unstoppable. So imagine that like a piston, completely unstoppable, and tiny bit of air coming out like that. So that's our volume velocity, speaker and a tube. It's not literally unstoppable, but let's just think about it like it is. In electrical terms, if anyone here is has done any electronics or something, when you have a source of power for a circuit, it can either be a voltage source or a current source. Voltage sources will go up and down, it can be sapped away. A current source is just like this powerful thing. So this is acting like a current source. And the pressure is the voltage that we record. All right, so we're putting in a slug of air, and it's literally, so if you think about this volume velocity, here's the tube that we're driving into the ear canal. The volume of air we're talking about is this little bunch of air right here, this little bit of air molecules right here, which are going forwards and backwards with a certain speed. Forward, backward. And that, again, it's going, here is all the air, it's in here now, into that cavity, and then it comes back out, and now it's here in the tube. So it's going in and out, in and out. We're adding air, removing air, adding air, removing air. The pressure will go up or the pressure will go down. Is everyone happy with that thing? Okay, so let's clarify one more time. What are the two things that make the pressure go up high? First thing is the size of the cavity. Which one makes the pressure go really big? A small cavity. What else makes the pressure go really high? Is it a brick wall at the end or a rubber balloon at the end? A brick wall. Okay. So imagine we come now to do tympanometry, and this isn't a tube. This is someone's ear canal. So here we've got an ear canal. There's the entrance to their ear canal. What do we find at the end of the ear canal? The eardrum that has the malleus, the incus, and then the stapes. Such a bad artist. Going here to the cochlea. Can everyone see that? Thank you. You're welcome. There we go, to the cochlea. And so this is the middle ear cavity here. Right. So let's put our tympanometer probe here at the entrance to the ear canal. So here's the entrance to the ear canal. I want to know, I don't really care about the ear canal. I want to know what's happening over here at this end. And I want to know, is this a rubber balloon or is it a brick wall? What is something that could make it a brick wall? Is there any sort of pathology that happens in the middle ear space? An ear infection. And what's a feature of ear infections? What do we find? What should the middle ear be full of? Air. And when you've got an ear infection, what can it be full of? Fluid. Yeah, it could be water. It could be pus. So it's full of fluid. Is it easy or hard to compress a fluid? It's hard. It's not impossible, but it is hard. So if I've got an eardrum like this and there's air behind it, yay, it moves, that's great. If I've got an eardrum and there is fluid behind it, it's a lot harder to move. The sound just doesn't get through to the cochlea as well. Does that make sense? Yay. All right, so what I'm interested in is this part of the story. Is it a floppy wall or is it a brick wall? And I want to measure that over here. So I'll get a result, right? And it will either be a high impedance or a low impedance. Well, am I down here at the eardrum or am I at the end of the ear canal? I'm at the end of the ear canal. Is the result I get going to depend on the size of that ear canal? Yeah, oh dear. Okay, that's a bit of a problem, isn't it? Because if I get a, let's say I get a high impedance, so let's say I get a low impedance, is that because, what would happen if I had a brick wall, which would give me a high impedance, but I had a really large ear canal, which would give me a lower impedance? How do I know what's the problem? What's the thing I'm trying to measure? How do I tell the difference between what is due to the size of the ear canal and what's due to the stiffness of the eardrum? How can I tell those two things apart? That's tricky. So we're not measuring at the eardrum, we're measuring at the entrance to the ear canal. So that is a problem. So fortunately, there's something I can do. So I mentioned that here in our probe tips, we've got 3 tubes. What are the 3 tubes? We've got the volume velocity source here. Here's our volume velocity source. We're measuring that whole thing with a microphone. That's the symbol for a microphone. I'm measuring with a microphone. What's the 3rd tube? It was the syringe-y type device, like so, that is, sometimes we pulled one of these apart once and it was literally a syringe that had a motor attached to it, like that. It works. So the trick we do is we say, okay, so here I am, this is my measure of admittance. So if I plot admittance on a plot like this, if I was to plot impedance, it would be upside down compared to the impedance here. So if I get a really large signal here from a high impedance and a low admittance, I would put a dot down here on admittance. So if I got a really large signal, I'd put a dot here. But if I got a really small signal, it means I've got a very high admittance. So the dot I would put would be up here. So let's say we've got a situation where I get a high admittance right here. That's the thing I've got. And I go, well, is that because the eardrum is floppy or is it because the ear canal volume is large? How do I tell? Well, the trick is, and this is the clever part. Are you ready? What if I make this floppy eardrum, what if I make that into a brick wall? If I just say, okay, let's just make it a brick wall and then measure. If I make that a brick wall, what's left? It's just the ear canal volume, right? Anything I measure is just to do with the ear canal volume. So one way I can make that a brick wall is to pump it up. So it's nice and floppy in the middle. If I inject a mass of air with the syringe and make it a brick wall, stiffen it up in one direction, then I will make it stiff. And when I make the brick wall, the eardrum into a brick wall by pumping it up, this is positive pressure, up to maybe, say, 200 decapascals. Or if I suck some air out of it down to like minus 200 decapascals, what's in the middle? 0 decapascals, which is 0 relative to atmospheric pressure. So this is like 1 atmosphere. So this is standard atmospheric pressure. I get that result. When I make it a brick wall by pumping air in, my admittance goes down to here. Not down to 0, but down to there. If I make it a brick wall by sucking the air out, the admittance goes down to there. And in fact, I can do that in a straight line and draw it across like this, and I get this sort of result. Oh, there's the mountain that we show the kiddies, right? So I've created this mountain. Here is 0 admittance, but how much of that is due to the eardrum and how much is due to the volume of the ear canal? When I've made the eardrum a brick wall, what am I measuring? Just the volume. So this here is the amount of floppiness, the amount of the determinant of the size of this that is due to the ear canal volume. Can you see that there? And so if I know that when the eardrum is a brick wall, it's this high, this much admittance, and when the eardrum's a brick wall over here, it's this much admittance. But in the middle, when the eardrum is not a brick wall, I've got this much. How much of the overall admittance is due to the eardrum? It's whatever's left, isn't it? So that part there is due to the ear canal volume. This part here is due to the floppiness of the eardrum and the middle ear. So that's a technique that we've got for telling those two things apart. That is the trick. We can separate the two things apart by using that syringe thing. So that's the process of tympanometry. We call this the ear canal volume, and we call this part here the static compliance. static compliance. All right, so let's think about the size of the pressure wave that we're recording in each of these cases. When it's a brick wall, do we get a high pressure? Yep. When it's a small ear canal, do we get a high pressure? Yep. So the size of the signal I'm getting here is, this would be, down this way would be a large pressure signal, and up here would be, in this direction, would be a lower pressure signal. Right. Does everyone get that? In fact, here's a little trick. You don't have to pay much attention to this, but here's a little trick. Instead of putting in a fixed volume velocity and measuring the size of what we get out, that would mean that in a baby's ear, we're going to get a really loud sound, and in a large adult's ear, we're going to get a really small sound. How about we just try and keep the sound the same level by automatically adjusting the size of the volume velocity we get, and that way no one gets their ears blown out by too much pressure. Does that make sense? So that's actually a little electronic circuit that says, how big do I need to make this to keep this pressure at some fixed level that I can measure? And so that's why, in this situation, that's a large pressure signal. What it means is we had to turn our volume velocity to be low to get a fixed size. And here we had to make the volume velocity high to get a fixed signal. And so that's the signal that we send to the dial, is just how big did we have to make the volume velocity to get our fixed pressure. So we go higher and lower, like so. All right, I'm going to turn this off now and show you some slides that explain exactly what I just explained. So here we go. What we have here is, this part here is a circuit diagram of what's going on. The letter Y means admittance, of course. Y for admittance. What's impedance? Z, of course. So Y is the floppiness due to the ear canal, so the sponginess of the ear canal. Small canals, not very spongy. Large canals, very spongy. And YD is the admittance or the floppiness of the drum. And if I've got a floppy eardrum that's allowing energy through, that's a large admittance. If it's a stiff drum, it's a low admittance. And where I'm measuring is at the entrance to the ear canal, way back here. U is obviously the volume velocity. U for volume velocity. There's only a certain number of letters in the alphabet, and they have to reuse them, so I'm afraid that's what we're left with. U is the volume velocity. P, thankfully, is pressure. So I measure the pressure when I put in my volume velocity. It's made up of two components, the eardrum and the ear canal. I can't tell them apart unless I make this be so stiff that it drops to zero. So by inflating the eardrum, this thing here drops away to nothing, and what's left? The ear canal. And so I say, oh, that's my ear canal volume. Great. Now let's measure the whole thing. And I get the sum of those two things, and by subtracting away what was the ear canal, I know what this bit is. It's a little bit of maths that the machine does, and we can see it on the graph there. I'm going to read the words on the slide, and hopefully now it will make complete sense. So at atmospheric pressure, the total floppiness that we record, the total admittance we record, is the sum of how large the ear canal is. So if it's a large volume, large admittance. If it's a low volume, a low admittance. And how floppy or compliant the eardrum and the middle ear system is. So if there's no fluid behind there, it's nice and floppy. If there is fluid behind there, then it's not very floppy, low compliance. What we do is we put our probe in here, seal that, so we seal it in here. We shove our volume velocity in here. There's that volume of air going backwards and forwards into here. We measure the size of the pressure change, and that will give us the total result. Then we use this syringe to pump some air in to make that a brick wall and disappear. So that's so hard now the admittance has gone to zero. All we're left with is what's the size of the volume. So now we've got a measure of the ear canal volume. And then we pull the pressure back, passing through zero so that this is able to move freely, and then we stiffen it up again at the other side. And we see, where did it move the freest? What pressure did it move the freest? If we've got air of the equal pressure on both sides, that's when it should move the freest. So when we go from being inflated to not inflated, when we get to atmospheric pressure, that's where we should get the floppiest part. And so we should get a little peak there. So the volume velocity is a little slug of air moving backwards and forwards really fast, 226 times a second. If it drives into a tiny ear canal or one with a brick wall at the end, we get a large sound pressure that we measure with our microphone. If it's a large cavity or a floppy eardrum, we get a lower pressure. And by just measuring the ratio of those two things, we can figure out what that overall floppiness is, and we can plot it out. So this is the graph that we get. When we put the syringe in here, negative pressures, positive pressures, and we sweep from one to the other, look at that. We get our little mountain, and we get some numbers that we can read off. And the numbers say that here is the peak that we recorded, and it happened close to zero. So that's good news. That means, yay, there's a peak. Firstly, it means the eardrum is moving. Secondly, it's near zero. So it means the air pressure on the inside and the outside of the eardrum are the same. That's great. This is made up of, obviously, two components. One component is how floppy the eardrum is. The other component is what's the volume of the ear canal. Can I tell those two apart? Yeah, look, when I make it a brick wall, this is just the ear canal volume here. Can you see that there? This much is due to the ear canal volume, and we can calibrate that to be, say, that's the equivalent of 1.1 cubic centimetres. So that's the volume of the ear canal, right there, 1.1 cubic centimetres. How big is the floppiness of the eardrum? Well, that's equivalent to 0.7 cubic centimetres. We can actually use the same units because it was saying it's as floppy as a volume of 0.7 cubic centimetres would be in terms of driving into it. So now we can tell the difference between that. Is that a good result? Yeah, we've got a peak. That's excellent. So what we get is a pattern of results. So here's our results that we look like that we can classify based on their shapes. So good news shape is this one, and we call that a type A. Yeah, you got an A. So type A shape there. Sometimes we do get a peak, but it's not as large as it could be. So if the peak was smaller, would that mean the eardrum is stiffer or floppier? Stiffer. And so we call that an AS. You could say AS for stiff, if you like. So here's the normal A, a shallow peak. It could be AS for shallow, stiff eardrum, shallow peak. There's a pathology which stiffens up the middle ear bones, and that's called otosclerosis. Have you heard of that? Otosclerosis. That's where the bones kind of fuse together a bit, and so they don't move as nicely. That stiffens up the system. So you could say AS for sclerotic ear bones. Shallow, stiff, sclerotic, AS. What if we still get a peak, but it's really, really floppy? So the stiffness that we measure of the eardrum is a combination of the eardrum itself plus the bones behind it. What would happen if you had a traffic accident and dislocated your middle ear bones? That's called ossicular discontinuity. It's a real thing. You shove a pencil down your ear, someone bumps it, ossicular discontinuity. That happens too. Now your eardrum is waving in the wind like this, super floppy. We still get a peak, but it's a really big peak because it's hyper compliant.
Does it mean it's broken?
The bones move past each other and need surgery to get them back in the right spot. All right, so there's our type A's. A, good news. AS, shallow, sclerotic, stiff. D, a deep tympanogram, discontinuity perhaps. So these are the A patterns. There's another pattern which is B. A type B means we didn't get a peak. There was no pressure at which the eardrum moved enough to give us a peak. That is the sign that there is fluid behind the eardrum. So if I get if this is like this but it's a flat line here, that's a type B, and that indicates fluid behind the eardrum. Everyone see that? And we call this, it's not just a type B, we need to add something to it. It's a type B low, because it's a low result. Can you see that? Type B low. There's another thing that I could get where I don't see a peak, and that's a type B high, which is up here. So imagine here I am doing my tympanometry, and in fact this eardrum has got a hole in it. So you get perforated eardrums. What is the volume that we're measuring? Is it just the ear canal, or is it the ear canal plus the entire middle ear cavity? Yeah, it is. And can this tympanometer actually see the eardrum move? No, because there's a great big hole in it. So our main cue for that has gone, and so the other type B that we can get is called a B high. So this is a B low, fluid behind the eardrum. B high means that there's a perforation. There's another peaky pattern here that you can see, which looks like a type A, but it doesn't happen at 0, it happens at some negative number. So if our peak occurs outside this box, this normative box here, if it occurs outside of there, we call it a type C. And that means that there's actually a bit of a vacuum right now in that middle ear. And that means we got the biggest amount of movement when we had a negative pressure on the outside because that matched what was inside. So that enables us to say, what was the pressure inside? Why do we get a negative pressure? Well, it happens just before an ear infection or just after an ear infection. Usually when you're coming into or out of that, you get a negative pressure. It means the eustachian tube, which joins the middle ear to the back of the throat, isn't working. So a type C here refers to eustachian tube dysfunction, negative middle ear pressure. So we get our results, we place the probe in there, it increases the pressure to make it a brick wall, decreases the pressure to make it a brick wall at the other end. We measure what component of our overall admittance is due to the ear canal, subtract off what is left, and that tells us we get a tympanogram that tells us what's left is the floppiness of the eardrum, which we can classify with these shapes here. Excellent. So how do we interpret that? Again, once more, here's our tympanogram. Type A, middle ear is functioning normally. Type AS, this one, shallow peak. The middle ear is stiff. The peak is low, but it's still a peak. Type AD, it's a deep tympanogram. That could mean a acicular discontinuity. The bones have given way. Type B, flat, no definable peak. We'll talk about in a second. Type C, negative middle ear pressure. Here's the perforation I was telling you about. Look at that. So we're not just measuring the volume of the ear canal. Suddenly it's the ear canal plus the middle ear. So it's a B high. We can have a B low. And so on. A low ear canal volume could mean that not only is there fluid behind the middle ear, but maybe there's wax blocking the whole tube and we've got just a stubby ear canal because there's a heap of wax in there. All right, we're running out of time. What I'm going to do is record this little section here on acoustic reflexes as a video, and I'd like you to watch that. You've got no lecture next week, so that's a heap of time in which to do that. The video will talk about acoustic reflexes. It will talk about the interpretation of them. I want you to focus on this bit and a little bit of this bit and a little bit of this bit and a little bit of that and a little bit of that, but not this stuff that says bonus material not for exam. This is, if you're interested, this is literally how we go side by side and figure out what is going on in that pathway from the acoustic reflexes. All right, so this will be in the video. Excellent. Thank you very much, guys. See you soon.